Which of the following molecules is not a structural isomer of methyl propanoate? The first thing that we should know is that esters and carboxylic acids can be structural isomers of one another. They both have 2 oxygens, and then your ratio of carbons to hydrogens is the same. So as a result, it looks like those 3 could all be structural isomers. The alcohol cannot be a structural isomer of an ester. So that kind of makes sense. Just double checking. Methyl propanoate is 1 carbon in the methyl, 3 carbons in the propanoate, so it's 4. Propyl methanoate 4, ethyl ethanoate 2 plus 2, 4, butanoic acid but 4. So they all seem very reasonable, and the answer is D. What is the IUPAC name for the compound alongside? They're 4, so that's not a big deal because they've told me all of them are butane, which is terrific. And then we're going to label from the side closest to the left or the right, or perhaps we will look at the fact that that is chloro and that is fluoro, and as a result, alphabetically, the chloro comes first. So it's 1, 2, 3, 4, and as a result, you land up with 2 chloro, 3 fluoro butane. Which of the substance is methyl pent-2-ine? I'm looking at this ine bit first and thinking of the functional group, and I'm looking for a triple bond. Double bond, alcohol, ketone or aldehyde, and because of the double bond O, and here is my only triple bond. So it seems perfectly reasonable. We can then double check it. We can say pent, which is 1, 2, 3, 4, 5. Yes, that makes sense. On the second carbon, there is a triple bond. Yes, 1, 2, 3. So that makes sense. And on the fourth carbon, 4, there is a methyl group. So all of that makes sense. Double checked. So A is burning of sulfur can be described by the following equation. Sulfur and oxygen gives me sulfur dioxide. How much will I get? How much sulfur dioxide will I get if I use 8 grams of sulfur? Well, sulfur has a molar mass of 32. So number of moles is mass over molar mass. So that's going to equal 0.25 moles. And therefore I'll get 0.25 moles of sulfur dioxide. 0.25 times by 22,4 is going to land up giving me 5,6, and therefore my answer is C. Which of the following is most polar? Now, let's just give ourselves a look at each of these molecules. That is a non-polar molecule in every way. It's totally symmetrical. Nitrogen, 1, 2, 3, non-polar molecule. Carbon, hydrogen, 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 and iodine. Iodine. Slightly polar, all right? And because of the electronegativity difference between the iodine and the chlorine. And then finally we get one of the most polar covalent molecules that we know, and that is the asymmetrical pyramidal nitrogen and hydrogen, which is going to be very strongly slightly negative at this highly high electron density area of the molecule, and these hydrogens are all going to be slightly positive. So that's your most polar out of that list over there. You can see this thing here resembles methane. It's really not terribly polar at all. Now you've got phosphorus hydride and arsenic hydride, both of which are hydrides, and one has a higher boiling point than the other. Now, the minute I'm talking about boiling point, I am going to need to say that the boiling point links to intermolecular forces. So when they start talking about the bonds, firstly, these are covalent molecules, non-metal, so it's covalent. So there's no ionic bond at all. Hydrogen bonds, it's a possibility because we are considering an intermolecular force, and a hydrogen bond is actually an intermolecular force. Covalent bonds is not an intermolecular force again. Van der Waals forces seems like quite a good idea. If there are stronger van der Waals forces, that means there will be a higher boiling point. So that looks like a very good idea. But what about this one over here? And you remember that hydrogen bonds actually only exist between hydrogen fluoride, water, and ammonia, and not between these two molecules over here. So the correct answer is D. Look at that chemical reaction. Which one of the following changes to the reaction conditions will have no influence on the reaction rate? Temperature always affects the reaction rate. Reducing the pressure, well, there are no gases. So if there are no gases, pressure makes no difference. So that looks like a very good answer. Concentration of the acid will change the rate, and using powder for a solid will change the rate. So B is your correct answer. You've got a chemical reaction between an acid and a solid, and it's too fast. So how are we going to make it slower, safer? We're going to use larger pieces of the solid. We're going to use a less concentrated acid and a lower temperature. Those things all slow down the rate, so C is your answer. And this equation is a common redox reaction. What is oxidized? I'm going to start with the really simple, and I'm going to say plus 2 plus 3. The oxidation number goes up. That is oxidation. What is oxidized? Fe2 plus. As easy as that. You could have done the whole equation if you wanted to. What is the story with this Boltzmann distribution? Firstly, you need to look what's on the actual axis. You've got your fraction of particles and kinetic energy. If lots of particles have got low kinetic energy, this is cold. If more particles have got more kinetic energy, as in T2, that is hotter. So the first thing is that T2 is hotter or greater than T1, which leaves me with only two options. Then what's this shaded region? The activation energy is the amount of energy, and all the particles on this side of the activation energy have enough energy to react. At the colder temperature, as you can see, actually it's very few. It's very, very few. But at the hotter temperature, lots of them are able to react. So the area X, yes, represents the fraction of particles that have enough energy to react. Yes, because they have more energy than the activation energy. So B is your correct answer.